Bismillahirrahmanirrahim, dear students. Welcome to the Electrical Engineering channel. This lecture is a part of the numerical methods course, and in this lecture, I will discuss solution of ordinary differential equations. So, ordinary differential equations are abbreviated as ODEs, and in ordinary differential equations, all derivatives are taken with respect to a single independent variable. If there are derivative terms with respect to more than one independent variable, then that type of differential equation is called as partial differential equation, and that is abbreviated as PDE. And if we have only one single independent variable, that ODE is that differential equation is called ordinary differential equation. So this is a general form of ordinary differential equation, and this is one example: 5d cube x over dx cube plus 3d square y over dx square minus 2 dy by dx is equal to 10. So there are two things which characterize the differential equations, and one is the order and second is the degree. So order is actually defined as the maximum derivative that is present in the equation, that is called order. So there is the third derivative of y which is present in this differential equation. So the order of this differential equation is 3, and degree is actually the maximum power of the derivative terms. So in all these three terms, the power is equal to 1. So the degree of this differential equation is equal to 1. Now we consider another example, and in this example you can see we have this differential equation. So the maximum derivative is actually single derivative. Okay, there is no second or third order derivative term in this differential equation. So the order of this differential equation is 1, but the power, maximum power is 2. So if we consider the first term, the maximum power of the derivative term is 2, so the degree of this differential equation is 2. In general, an ordinary differential equation can be written in this form. So this is nth order derivative uh, which is present in the first term plus n minus one order derivative will be present in the second term, and so on. And in the second last term, there will be first order derivative, and in the last term, there will be no derivative, and that sum of derivative terms is equal to any function of x, right? So this is the general form of an ordinary differential equation, and there are several methods of solving differential equations. For example, homogeneous and non-homogeneous method, eigenvalue method, Laplace transform method, and so on. But in today's lecture, I will discuss the solution of differential equations by homogeneous and non-homogeneous method. So in solving the ODEs using this method, we have actually two solutions. First solution is called homogeneous solution. So that is represented by YH, and second solution is called particular solution, and that is represented by YP. So we have to add these two solutions to get the overall solution of this differential equation. And the homogeneous solution is also called as complementary solution, and YP is called particular solution. So this is an example which we can solve using this method, and this is an example of a non-homogeneous ODE. So if the term on the right hand side is non-zero, then this type of differential equation is called non-homogeneous differential equation. If the term on the right hand side is equal to 0, then this differential equation will be homogeneous differential equation. So let's solve this ODE, and we have to denote d by dx by capital D. So it will become d square, and we can take y as common from the left hand side. So when we take y as common, it will be d square by dx square minus 3d by dx plus 2. So d by dx can be replaced by capital D, so it will be d square minus 3d plus 2, and y is taken as common, and right hand side is equal to 5. So first we will evaluate the homogeneous solution or complementary solution, and we have to equate this differential equation to 0, because whenever we have a 0 at the right hand side, the differential equation will be homogeneous. So we have to make this homogeneous, and then we will get the homogeneous or complementary solution. So let's equate this equation to 0, and this equation we will get at the end, and this is called characteristic equation. and we have to find out the roots of this characteristic equation. And the roots of this different characteristic equation are d is equal to 1 and 2. So we can do this separation, and d is equal to 1 and d is equal to 2. So these are the two roots. Now, depending on the nature of these roots, we have to evaluate, or we have to decide the general form of the homogeneous solution. So if the roots are real and distinct, then the homogeneous solution will be of the form C1 is e raised to power r1x plus C2 e to power r2x. So there is e missing over here, and the C2 e2 raised to power r2x plus so on. Right, so r1 is the first root and r2 is the second root, and c1 and c2 are the constants. So this is the general form of the homogeneous solution if the roots are real and distinct. So here we have real and distinct roots. The roots are real numbers and they are different. Both are different from each other. Second case is the roots are real and equal. So if the roots are real and equal, then homogeneous solution will be of this form: yh is equal to c1 plus c2x e raised to power r1x. So if we have only one root which is repeated, for example d1 equal to d2 and both are equal to r1, so then this will be the general form of the homogeneous solution. C1 and C2 are constants. Third case is the roots are complex. So if the roots are complex and they will be in pairs, so each pair will have two mutually conjugate terms. So if we have two roots and they are complex, then first root will be a plus b iota, second will be essentially a minus b iota. So they will be complex conjugate of each other. And in this case, the general form of the homogeneous solution will be e raised to power ax m cos bx plus n sin bx. So a is the real part of both the roots, and b is the imaginary part of both the roots. M and n are constants. So these constants, either c1, c2, or m or n, they will be evaluated by using the initial conditions. So we will be given initial conditions, then we can substitute those initial conditions in this solution, and we can find out the constants m and n, or c1 or c2 in this case. So that will give us the complete solution of the ordinary differential equation. So let's solve a couple of examples, and then we will be familiar with how to solve ODEs. So this is one example, and we have first order ODE. So 3 dy by dx plus 2y equal to e raised to power minus x, and we are given the initial condition y0 is equal to 5. So let's evaluate the characteristic equation first. So replace dy dx by d and take y as common. So we will have 3d plus 2 equal to 0, and d will be equal to minus 2 by 3. So simply our root is d equal to minus 2 by 3, and the general solution or homogeneous solution will be c e raised to power minus 2 by 3x. Since we have only one root in this case, and this is a first order ODE, so that's why we will get only one root. So now we will evaluate the particular solution, and the particular solution can be evaluated again by observing the nature of the function at the right hand side of the equation. So if at the right hand side we have such a term z e raised to power omega x, then the general particular solution will be a e raised to power omega x. So, for example, in this case, we have e raised to power minus x. So, our particular solution yp will be equal to a e raised to power minus x. So, a is a constant, and e raised to power minus x will come as it is. And if we have a sinusoidal function at the right hand side, for example, z sine omega x, then the general form of the particular solution will be a sine omega x plus b cos omega x. Similarly, if we have some constant times cos omega x at the right hand side, again we will have both the sinusoids, a sine omega x plus b cos omega x. So general form will contain both the sinusoidal terms, and if we have both cos and sine functions at the right hand side of the differential equation, then again our general form of the particular solution will be like this: a sine omega x plus b cos omega x. And in the third case, we can have a polynomial, and if we have a second order polynomial at the right hand side, then the general particular solution will also be a second order polynomial, but the constants will be different. So ax square plus bx plus c, and here you can see that we have a missing term of x raised to power 1, but in the general particular solution all terms will be present and their constants will also be different from those which are present in the ODE. So if it is a third order polynomial, then we will have third order polynomial as well in the general particular solution. So I hope you have understood this concept. So let's go back to the original problem and solve it. So this is the general form of the particular solution a e raised to power minus x. Let's put this solution in this original ODE. So it will be 3d by dx a e raised to power minus x. So put this general solution in term in place of y, and it will be 2 times a e raised to power minus x equal to e raised to power minus x. And let's evaluate the derivative. So it will become minus 3 a e raised to power minus x plus 2 a e raised to power minus x equal to e raised to power minus x. And we can uh, take e raised to power minus x as common and cancel um, the left hand side and the right hand side. Then we will have minus 3a plus 2a equal to 1, and a will be equal to minus 1. So put this a in this general particular solution. So yp will be equal to minus e raised to power minus x. So we have obtained both the solutions, and then we have to add these solutions. So this is homogeneous solution, this is particular solution. Now we have to evaluate the value of this constant, and y0 is equal to 5 is the initial condition which is given to us. So let's put this initial condition in this equation. So y at 0 will be equal to c e raised to power 0 minus e raised to power 0. So y at 0 is equal to 5, it will be c minus 1, so c is equal to 6. Let's put this back in this original solution. So y is equal to 6 e raised to power minus 2 by 3x minus e raised to power minus x. So this is the overall or complete solution of this ODE. So let's solve another example and then we will be done with this lecture. And we are given a second order ODE in this example. So let's first develop the characteristic equation 2d square plus 3d plus 3.125 equal to 0. And the roots of this characteristic equation are r is equal to minus 0.75 plus minus iota, and these are initial conditions which are given to us. Y0 equal to 5 and derivative of y at 0 is equal to 3. So if we have first order ODE, then there will be one constant and we will need one initial condition, right? So we will need only one initial condition because we will have only one constant. For example, in this problem. And if we have a second order ODE, then there will be two constants and we will need two initial conditions. So if we are given two initial conditions, then two constants can be evaluated. So this is our YH because our roots are complex. So e raised to power minus 0.75x m cos x plus n sin x, right? Because the imaginary part is equal to 1. So this is cos x and this is sin x. So the constants are named as k1 and k2 in this example, but that will not be an issue. And let's evaluate the particular solution now. So the right hand side of this ODE is actually sin x. So general particular solution will be a sin x plus b cos x. So let's put this particular solution in this original ODE, and we will have 2d square by dx yp plus 3d by dx yp plus 3.125 yp equal to sin x. Now let's evaluate the derivatives, all these derivatives, and at the end we will combine the terms for sin x and cos x, and this is equal to sin x. Now comparing the left hand side and the right hand side, we have sin x term at the right hand side, so it means this term is equal to 1, and there is no cosine term at the right hand side, so this term will be equal to 0. So we have two equations and we have two unknowns, and by solving these two equations simultaneously we can evaluate a and b. So a and b are evaluated as 0.109 and minus 0.29. So put these a and b values in this general particular solution. So yp is evaluated as is written over here. And now let's evaluate that complete solution. So y is equal to yp plus yh. So this is yh, this is yp. And here we have two constants k1 and k2. Now we will use initial conditions. Y0 is equal to 5. So let's put y0 in this equation. So y0 is equal to e raised to power 0, k1 cosine 0 plus k2 sine 0 plus 0.109 sine 0 minus 0.29 cos 0. So it will be K1 minus 0.29, right? So here we will have 5. So K1 minus 0.29 is equal to 5. So K1 will be equal to 5 plus 0.29. So this is K1. Now we will use the second condition. So we will have to take the derivative of y with respect to x, then put this initial condition. We will put x equal to 0, and then we will put dy by dx equal to 3. And then we will again solve that equation. We are given the value of K1. So K2 can be evaluated. So K2 is given as 6.86. So our complete solution will be this equation, and K1 and K2 values are already evaluated. So that is all about our today's lecture, and I hope you have enjoyed the solution of ODEs using homogeneous and non-homogeneous solutions method. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.